Okay, so I believe we had spent some time on bending moment, shear force diagram. We'll continue with it because this one is very important. So we are continuing with bending moment, shear force. So it is called axial force, shear force, and bending moment. BM diagram. This is the. We will continue with this. This is a simply supported beam, means the support is such that there will be only three reactions. Why it is called simply supported? Because the support is such that there will be only three reactions if the loads are applied to it in any manner. Loads are applied to it in any manner. There will be three reactions, and these three reactions can be solved by equations of statics, equations of equilibrium. Statics are equations of equilibrium. So such problems are called statically determinate. So we are talking of only bending moment diagrams, shear force diagrams, and axial force diagrams for determinate structures. Determinate, statically determinate, not indeterminate. Okay. So let us say that we have in the center at L by 2, this is L, length is L, at the center I apply a bending moment M naught. Now how do you apply this bending moment M naught? A moment whose vector is perpendicular to the plane of the paper. So there are various ways in which this bending moment can be applied. Diagrammatically this is all right, that you have applied a bending moment. Now bending moment also, a moment also is a free, called free moment. Moment is, it can be applied anywhere, although I am saying that it is applied in the center. So here I can apply this, I can have a small I can apply, this can be A, this can be again A, this means this length from here to here. So I apply a couple, equal and opposite forces, and the distance between them is 2A, such that, so I apply such that P into 2A is equal to M naught. So this is a possibility. I can, now can you apply this? How do you apply a force like this? Horizontal force. Okay, P into 2A, I will keep that. I think you should learn how will you apply this, a force. So there are various ways. I think this is where I am poor in experimentation, but then you should be able to, innovation comes only through experimentation. So you should be also a good experimentalist. In addition to being a good theoretician, you should also be a good experimentalist. You should know how to apply this load. It is not that you have to apply. So here you can have a stud which is welded over here. You can weld a small piece of, a small rod to this beam. Similarly, you can weld here also. Welding, you can do the welding. So this is length is A. You can put a string and you can have a pulley here. Frictionless pulley and apply P to a load here. So that will pull. This will be this string will be under tension. So this P will be everywhere, it will be, if there is no friction, so this everywhere it will be P. And similarly here also you can do the same thing. You can put a pulley force. Pulley means there has to be some support, and then wait. So this will also be under tension, and this will be. So these are the ways in which this torque, this moment can be. This is not torque. This is bending moment. Sorry, it's not torque. Torque has to be applied along the axis of the member. When there is a difference between bending moment and torque. So teachers also make mistake. It is not torque. It is a bending moment. Bending moment, torque you have seen. A shaft under twist. A shaft, a circular shaft under torque. So that is applied along the axis. The vector is along the axis. Here it is not along the axis. Here it is perpendicular to the axis. This bending moment. So, okay. So this is a possibility. So moment is applied. Now I want you to draw axial force, bending moment, shear force diagram for this. I have not drawn. So first of all, you have to draw the free body diagram. So free body diagram. So this is a rod. Very neatly. This point is A. This point is B. This is a roller. So there has to be only a reaction upwards. This is a hinge. So there will be two reactions. And let us say it is VA and HA, and here it is VB, and here we are applying M moment, M naught. Because of this is a free body diagram of the, and what is the free body diagram of the support, which is not normally given in the, what about the support? Support is here. You have removed the support. So support will be, and similarly here is the support. You have removed, you have cut through the support. So this will be subjected to VB. Here this will be subjected to VA and HA. Equal and opposite. Here Newton's third law comes in this. Equal and opposite. So this is the free body diagram of the support, the hinge and the roller, and this total is the free body diagram of the beam. Is it okay? Have you understood? So although we never draw this, I don't know whether this is given in the book. Support free body diagram, is it given in the book? Check up. So this is how the loads are, because once you are applying, then the load has to, okay. So now you please find out what is the values of M naught. So first thing is VA plus HA. Horizontal force must be 0, so there is only HA. Then VA plus VB is 0, there is no vertical force, so this is equal to 0. Take moment about any point, I am taking moment about point A. So about this, M naught is a free vector, so M naught clockwise minus VB into L equal to 0. These are the three equations of equilibrium. So this you have to write clearly, then only you can find out. Now HA first one is giving, so from here you get M naught by L. VB equal to M naught by L. So directly you got the value of VB here. Is it okay? M naught by L. And go back, go to here, from here to here, and then you can get VA equal to minus VB. That will be equal to M naught by L with a negative sign. So all the three reactions are known now in terms of m naught and the geometry of the beam. What is the geometry of the beam? Length and of course cross section is not coming here. Modulus of velocity, moment of inertia is not coming here. Area of cross section is not involved. When will these quantities come in the picture? Area of cross section, moment of inertia. When will that come? You have solved some problem in axially loaded member. When did the area of cross section was required? When did it you require the area of cross section for computation? Yes, stress is strain. Okay, but before that, how will you find out the forces in the member? When the problem is statically indeterminate, then you have to consider geometrical deformation. We have not considered because this beam will, under the moment, this will deflect, this will deform. We have not considered deformation of the beam. We have not considered deflection of the beam. So we have considered here only equilibrium. How many laws are there for mechanics of solids? Three. Equilibrium. Then second one is study the deformation, and then the stress strain law or force displacement law. Relationship between stress and strain or between force and displacement. These three are required. So when do you go to the other two steps? When the problem is statically indeterminate. When the problem becomes indeterminate, then you will be required to use geometrical properties. The cross-sectional modulus of velocity, things like that. Here we have not. Equilibrium doesn't require anything. Equilibrium, it is very simple. So if it is statically determinate, you don't have to worry about other properties of the. Okay. So anyway, you have got this. Now you have got all the. So now my problem is that. So now you have a beam, and then you have VB is equal to VB is same. So VB direction is correct. So this is m naught by L. At VA, the direction is VA equal to minus m naught by L. So whatever you assume, it must be reversed. So VA is like this, downwards. At A, the force will be downwards. You can draw from top or you can top it, because I have written here A, so I didn't have space, so I have drawn it up. And then it So this is at a distance x. So what is the positive shear force? Positive shear force is our shear force is like this. I have taken on a positive x base, shear force upward is positive. So this is my diagram. So yes, please. So what will be this equal to? So that one will be equal to. So therefore V will be equal to m naught by L, positive. As per this convention, upward and this is downward. There is no other force. So in order to keep this small piece of rod in equilibrium, vertical equilibrium, you need this. V must be equal to m naught by L. And then this is independent of x. Although I have written here x, function of x at a distance x, but even if you put anywhere, you put this anywhere, vertical force will remain the same. Even before this m naught or after this m naught, it will not change. It will not change. So this is very important here. There is no change of shear force from positive to negative here. So here I will draw a shear force diagram which is positive m naught by L. Now how many people understood this? It will be positive shear force throughout the length of the rod, throughout the length of the beam. There is no change. See, because even if I take over here m naught, vertical equilibrium, m naught will not come in the picture. Is it okay? We are not taking moment equilibrium. We are taking only vertical equilibrium in order to find out this. So there is no vertical force anywhere, and this is only force. So throughout the length, it is m naught by L. So shear force diagram, constant shear of m naught by L. The whole rod will be subjected to a constant shear of m naught by L. Now please go to bending moment diagram. BMD. Yes, BMD will be what? Now at this same section, what is my positive bending moment? My bending moment diagram on a positive x base is like this. Is it okay? Whatever I have drawn. So you take moment about this point. Moment of V will be 0, and therefore this m will be equal to m naught L into x. So therefore you get mx equal to m naught by L into x. How many people understand this? So anyway, but the thing is, now here there is a problem. This I will have to write that this expression is okay till x is less than L by 2, because m naught will come later on. So I will write here this expression is alright provided x is less than what? L by 2. Because once I take x over here which is beyond this, then I must consider m naught also. See, till at this point x will be, because m naught is not there. M naught is acting at the center, so it will matter here. Now afterwards, when x is more than L by 2, so let us take the free body diagram from the left side. Silence please. Let us say this is the center, so there is a bending moment here m naught, and this is my x. So this x is more than L by 2. Is it okay? At this cross section, and my bending moment here is m. I want to find out this mx. Is it okay, free body diagram? This is the total length, this is the length which is going beyond m naught. M naught is acting here, and then I have taken x beyond center point, and so I want to find out this value up. So I take moment about this point, so I get this equal to mx will be equal to m naught L into x, which is opposite, and then what? Minus m naught. Minus m naught, because m naught is coming here. So at this point, take moment about this point. So this m naught divided by L into x minus m naught, because this is acting in the clockwise. So clockwise is, otherwise you have to write on the left hand side. So this is equal to clockwise, anti-clockwise. So then this is equal to, and that becomes equal to x minus 1. What is this? M naught can be taken common. So m naught x by L minus 1. X has to be taken more than L by 2 here. So at x equal to L, this is equal to 0. X equal to L, this becomes 0. And then at x equal to L by 2, how much? Minus m naught by, so at x equal to L equal to L by 2. At x equal to L by 2, so this will be 1 by 2 minus 1, so minus m naught. And similarly from the first expression which was here, this we are going upward. Now for the first expression, so at x equal to L by 2, this is m naught by 2 again, but positive. So my bending moment diagram here will be going like this. From this it is positive, so it is going at x equal to 0, it is 0. Is it okay or not? So it is a triangular linear variation, it is going, and this value is m naught by 2, positive. Then we find here that it changes, it comes down and then again it goes, so this is again m naught by 2. And what is this total value? M naught by 2 and m naught by 2 equal to m naught. So total moment is m naught at the center, half up, half down. So there is a change. If you see, it is going up, and the moment this m naught comes, there is a jump. So wherever, just like I think we had drawn last time bending moment shear force diagram, when there was a central load, vertical load, there the shear force changed suddenly. This value also, this line cannot be vertical, actually it is an inclined, slightly inclined line, because the expressions are valid not at x equal to L by 2 exactly, they are valid less than L by 2 or more than L by 2, slightly. So actually this line has to be inclined slightly. You cannot find out exactly at L by 2, that is a point of similarity. There is a change, you have applied a concentrated moment, but then there is a change total from plus m by 2 to minus m by 2. So this is negative and this is. So this is BMD diagram, this is shear force diagram. So remember, wherever you will have a moment, concentrated moment in any bending moment diagram, whenever you draw, there must be a change from positive to negative or from negative to positive. I am coming to that now. So one is, I have done this with a L by 2, this is in center. So this, all the three diagrams are drawn. So this is very important. Remember, if there is a concentrated force on the beam, wherever it comes, there must be a sudden change in the shear force diagram. Whenever there is a concentrated moment, there must be a sudden change in bending moment diagram. And the change value must be equal to the total moment or total shear force or total load applied at that particular point. Is it okay? Total moment, see, from plus to minus m naught it is coming. Similarly, in the case of load, it was coming from minus p by 2 to plus p by 2 or vice versa. But these diagrams are drawn based upon convention. Now, what kind of this diagram that moment and shear force that I have taken, this kind of moment produces tension at the top of the beam. So it will bend. Is it okay? I think that I have shown earlier. So when there is a small beam element of length delta x, I have cut this at two sections x. So over here it is x and here it is x plus delta x. So I have separated. So my bending moment diagram is like this. Here m and here is also m. Again, whenever on this small beam which is having a small depth, the shear force diagram here, positive shear on the positive face will be like this shear, and on a negative face the shear will be like this. Is it okay? So this is my shear force diagram. So shear, how will you get this kind of shear? Upward. See, on the left face you are getting upward shear. This one is very clear to understand that this will produce tension at the top and compression at the bottom, because this will be bent like this. Under positive moment, so here it is a tension, here it is a compression. And then you must have seen that we are trying our positive bending moment, we are trying on the tension side positive bending moment, on the compression side negative bending moment. So there is a physics involved in this. I am not drawing it just like that. So you should also see under this you should also try to visualize what happens to the beam as such, because beam is having some depth. What happens to the beam? Silence please. What happens to the beam is simply supported and you have applied a bending moment here, a moment m naught. So how it will deflect? What will be the shape of the beam under the action of this? This also you must visualize. So if this is the axis of the beam, see this is trying to rotate the beam like this. So over here it will go something like this, because here it has to be 0, here it has to be 0. How will you get tension at the top? So this is the deflected profile. This is the deflected profile. Profile of the center line of the beam. Center line means center axis of the axis of the beam. It will deflect something like this. The beam will deflect because you are applying a bending moment here, bending its center. So at this point it is not going to deflect. Okay. But then, so here it will be 0, here 0, here it will go up and it will go like this. So you should always think of this, because then you will not draw wrong bending moment diagram. So then you can see, yes, the bending moment must be positive here. This is tension at the top, this is tension at the bottom. What is this point? Center point. See, suddenly bending moment is 0 here. Was it not 0? Because it has to come and cross axis. From positive to negative means it is coming to 0 axis. Here it is 0 in the center, because I told you this line has to be inclined. So at this point, what is the bending moment at the center? It has to be 0. It cannot be either, first of all, 0 in the sense, that means it is passing through the axis. It is not 0. Actually, you have applied a bending moment which is m naught. But then it is passing through the center from plus to minus. So it is passing. So there you have, the curvature of the center line of the beam, the axis of the beam, the curvature. So here if I take 2 points, the curvature here, center of curvature is here. And here if I take 2 points, the center of curvature is here. Do you agree this? For this curve, what will be the center of curvature? This will form some curve, not necessarily circle, but it is going to form a curve. So if you take 2 points and draw, so they will meet somewhere. So that is called instantaneous center of curvature. And on this side, so at this point the center of curvature, so it is going through from positive to negative. So this point is called where the bending moment changes its sign. The point where the bending moment changes its sign from positive to negative or from negative to positive. Is it okay? This is the point. It is called point of contraflexure. Point of contraflexure, because this is flexure, this is bending in this way, this is bending in this way. The point of contra dash flexure. Is it okay? Point of contra bending, flexure and bending, they are used synonymously. The words are flexure and bending. So they have the same meaning. So it is called point of contraflexure. Contraflexure is one word, hyphenated word. So contraflexure. Why it is called point of contraflexure? Because curvature is changing here. This is the point where curvature of the curve is changing. Curvature of which curve? Deflected profile. The beam which is deflecting is changing. Is it okay? So remember, whenever you draw any bending moment diagram, shear force, note down also points of contraflexure. There will be situations where this will come. Now, maybe we can have 5 minutes break, and then we can start the next.